Hello guys, welcome to my YouTube channel. So this is one of the um question that is arises into the analog design interview as well. So why MOSFET is used in saturation region instead of linear region during the amplification process? So firstly, we will be looking into the how the MOSFETs looks like. So basically, MOSFET is having majorly three terminals, that is drain. We are taking our NMOS as a reference. So this is our NMOS. Okay. So okay. So this is our drain. This is our source. This is our gate. Okay. And the ID current is given in this fashion. And this is our ID current. Okay. Sorry. Okay. So in this case, the MOSFET is going to work out in three regions. Those are as below. The regions of MOSFET. Okay. Regions of MOSFET in which it is going to work out. So first region is your first region is cutoff region. Cutoff region. Okay. Second one is linear region. And third region is saturation region. Okay. So coming to the first region, that is our cutoff region. Okay. First region, that is cutoff region. So draw the line. Okay. So what happens in the cutoff region in the sense your VGS, sorry, yeah, here only we can add, right? Just select this. Okay, just move this up. Yeah. Okay, the first region is cutoff region. In cutoff region, your VGS, as I said, what is VGS? The sense the VGS, gate to source voltage, VGS in VGS is less than VTH. Your VGS is less than VTH. So what VTH? VTH is the threshold voltage. Threshold voltage. So this is a minimum voltage. This is a minimum voltage to form the channel. Okay, minimum voltage that's need to apply over gate to source terminal, gate to source terminal to form the channel, okay, the channel. So in this case your MOSFET is going to be off state. MOSFET is off. Okay, so MOSFET is off in the sense your ID current is going to be 0. So ID current equal to 0, it means there is no formation of any channel, right? Let's draw this one. Okay, next thing is your next one is a linear region. Linear region. Okay, draw the line. Okay, in this linear region, your VGS, just change the color. Your VGS is greater than VTH. It means MOSFET is on. MOS is on state. Okay, it means your, and one more condition for linear region is your VDS is less than VGS minus VTH. Okay, this is one of the important condition that keeps your MOSFET in linear region. So in this case, your ID current is given as mu Cox W by L VGS minus VTH into VDS minus VDS square by 2. So this is your ID current. Okay, just draw the rectangle across it. This is also one of the important equation that's comes in the linear region. Okay, so this is your ID current. Next thing, if you want to get the linear region, so linear region is going to be uh, taken into the consideration when your VDS is much more smaller. So if you put VDS much more smaller in this equation, your VDS square terms is going to be ignored. Okay, so ultimately we will be remained with your ID. Just change the color. Your VDS is smaller. Okay, so your ID current will be mu Cox W by L VGS minus VTH into VDS, where VDS is a drain to source voltage and VGS is the gate to source voltage, and mu n is the mobility of electrons, Cox is the oxide capacitance, W is the width, and L is the length. Okay, so these are the terminologies you are supposed to take into the mind. Let's draw one of the rectangle for this as well. Yeah, next thing we are going to find the gain. Okay, for to find the gain, how to find the gain, that is one of the biggest question, right? The gain calculation, gain of an amplifier is given as below. Just draw the line. Okay, so gain is given as E equal to gm by gds. So we will be looking into what actually gm is a transconductance. Okay, transconductance conductance. And what is gds? GDS is the output conductance. Output conductance. Okay. So your GM. So GM is given as dou ID divided by dou VGS. Okay. This is a for formula to calculate our GM. This is a GM. And how GDS can be written? GDS is given as dou ID by dou VDS. As you can see over here, GM in the sense transconductance. Sorry. Okay. So GM is a transconductance. We are going to partially differentiate your id current with respect to your input voltage, right? Gate to source voltage is the input. That's why the terms trans come over here. Trans in the sense output is going to be differentiated by some of the input properties. So id is going to be differentiated with respect to gate to source voltage, and gds is output conductance. It is your output current is going to differentiate with respect to your vds. Okay, so let's calculate gm and gds for our linear region. So as I said, gm is given by dou id by dou vgs. Okay, so what was your id? So this is our id. If you differentiate with respect to vgs, we are going to remain with mu n cox w by l vds, right? This is going to be 1, and ultimately we will be remaining with mu n cox w by l vds. So mu n cox w by l into vds. So this is what we are going to get ultimately. Okay, next thing, let's calculate gds. So EDS is dou ID by dou VDS. Going to the same equation, if we differentiate this equation with respect to VDS, we are going to remain with mu n cox W by L VGS minus VTH. We are going to remain with mu n cox W by L VGS minus VTH. Okay, let's draw the rectangle for this. Yeah, done. Next, calculate the our gain. So next, our gain is given as gm by gds. Okay, so gm by gds in the sense, so if you divide this equation with respect to this, we are going to remain with this, both the terms going to get cancel out, and we are going to remain with vds divided by vgs minus vth. So we are remain with vds divided by vgs minus vth. But we are known that in linear condition your vds is less than vgs minus vts, so this quantity is less than 1. That's why your amplification is not going to happen. To amplify anything, your gain should be greater than 1. So that's why, so this is the reason MOSFET is not being used, not being used in the linear region during amplification. During amplification. Okay,